Oh yeah, you can. I'll start a file.
Oh, sorry. So
You're here.
I'm here. Trying to study for the final for master. Thank you. I figured it out. I think it's my gallbladder.
Oh no.
I need to talk to you about that too. I might have hepatitis removed.
Yeah.
I have a HEDA scan tomorrow
No,
to check
no.
it's functioning because they didn't see any ultrasound. So
Yeah. But yeah, I mean, so you have until the end of winter quarter to get the incomplete done. And, yeah, finish your grade. So whenever you want to take the final, we can just schedule that. I think the testing center should be available too. They have a little bit more availability, so that should work out. And then yeah, if you want to just meet individually and go over anything from last quarter,
yeah,
obviously
I would love
I'm happy.
that because I don't.
Yeah, you were kind of out the last like week or two, I remember. So.
And I don't have access to 320
Oh.
or to last quarter.
Oh, you
anymore.
don't?
No.
I thought you had it.
It's locked for me.
Okay, I'll email Blackboard because it should be open for you if you have it incomplete. But yeah, I'll double check.
Okay, thank you.
And yeah, I'm glad to see you today.
I found one that was actually like $2.89. I think it's like, I think it was like an iPad Air 10. I don't know if it's older now. It was like $2.89. Yeah, that's crazy. Posters there. I know, I'm probably gonna do it like tomorrow. Because I'm gonna do like stuff like that. Honestly, I was school class break. I have everything to do. Yeah. What time is it right now? Oh, okay, I was gonna go out. I can do that later. Yeah, I can do it during the break. Okay. I'll probably just get something from upstairs. Unless you want to get something from the... Yeah, we'll do it. If it's not that much. Is there energy drinks? Like... I haven't figured out what notes I have to use, so I'm just going to use the regular. Yeah, I'm just using like the regular.
All right, welcome. Happy Thursday. And so again, I know we're still kind of in and out. A few people have already let me know that they're sick or whatever. That's fine. You don't have to worry about attendance too much, right? Y'all are my 200 level class. I already know y'all, and then the new people that have joined, I've figured you out pretty quickly. So yeah, don't stress too much. Just again send me an email. I'll make sure your attendance is taken care of for everything. And again, if you need to do lab at home this week, you can. Right? It is a just WebMO based lab, and we'll play more around with that WebMO next week too when we do MO theory. So yeah, just have fun at home, play with it all you want. All right, so our plan for today is hopefully I'll get through like our main content material in the first hour lecture, and then I'll use our recitation time. We'll kind of talk about the paper. We may just go into a little bit in detail about this racemic mixture issue that we'll bring up as we talk about isomers. And I did put out our kind of in quote quiz. So it's just a check-in. I'm using that to do attendance today, and in quote attendance, right? So I'm just kind of double checking who's here. So just turn those in, whenever. It's just like about yourself. It's not a real quiz. If you're not here today, right, don't panic. We'll just fill those in another day. Not a big deal. So we're starting a pile over here, and then, yeah, just get them in by the end of recitation. Yeah, so we're going to finish up Chapter 8. So like I said, hopefully we'll finish that in the primary first hour of lecture. And so let's recap. And if you missed out on the Vesper sheet, I forgot them in my office, so I'll grab them during the break if you needed the Vesper sheet. I did give it out last quarter. It's just seeing it again. All right, so quick recap, right? We were looking at our Vesper sheet. So we've just been kind of running through our hybridization, right? So basically, this Vesper sheet is a great cheat sheet for telling us what the shapes are going to be. And then I was going to point out this thing here, because I don't know why it mentions this, that it says it fails for transition metal compounds. I don't really find that to be true. I find that this will be really helpful forever. So I don't know why they made that statement. But anyway, so right, quick recap. Sort of saying, okay, if we're examining anything, we're treating something as our central atom. It has 2 lone pairs. We saw that was sp hybridized. Again, just going back, reminding ourselves of the shapes. Oh. So write sp. Sorry, I didn't write that one apparently. So it just made those 2 lobes like we saw. sp2. And then, right, we saw 3 electron pairs, sp2. We mixed 1 s, 2 p's to give us our 3 lobes. So write 3 things mixed for 3 lobes. Then we kept moving on. So then we did, right, 4 electron pairs. Again, examine any central atom. See that there are 4 things attached. sp3. Yeah, question.
Quick question about sp3. So we used carbon dioxide as an example. And I know the oxygens exhibit sp3 hybridization.
Double check that, right?
sp2.
Yeah, so they exhibit sp2 hybridization.
So does the central carbon exhibit the same sp2 hybridization?
So remember the central carbon, so we go back to that example of CO2 here. So central carbon, 2 things attached to it, right? No lone pairs. So what's the hybridization?
sp.
sp. Yeah, so it's just sp.
It's because it has no lone pairs.
Correct. Yeah, so it's just, right, there's no lone pairs. And so, right, that's the whole point, is you're seeing the power of this, right? So you're looking at the structure, okay, there's just 2 things attached, no lone pairs. I know it's sp, I know those orbitals involved, so things are starting to really come together here. So back to sp3, like we said, okay, 4 things attached to it. Again, could be lone pairs. It's going to be in this geometry, right? That's also what we're saying. Where did I put all our pictures? sp3. So again, now 1, 2, 3, 4 things mixed together to give us 4 lobes. And so like we mentioned, once we get onto these sp3d and sp3d2s, there are actually no d orbitals invoked. It's really just p orbitals, and if you want to talk about it more in detail, how this mixing happens, we can. Otherwise, we just accept it as the shape name. And so we looked at, again, 5 electron pairs, right, our general electron geometry. The naming just tells us, again, we have 5 things kind of mixed, and to give us 5 lobes, like we saw in this shape. So our 5 lobes. And then our sp3d2, again, only made up of p orbitals, but this 6-membered shape, yeah.
Why are they called sp3 and stuff? This is like always a big s orbital and p orbital.
Well, so that's like the tricky thing about the naming is, right, these are reflective of what is actually mixed together, right? But then that naming breaks down for these, right? Because that's where we have to get into like higher order symmetry arguments. That's where point groups come into play. But we don't want to get into all that right now. But again, if you want to talk about that separately with me, we can, and you might, understand it a little better. But it just kind of depends where you are and how you're feeling. And so let's continue. So we were here in our 6 electron pairs. So again, sp3d2. So we're kind of pretending that there's 2 Ds, or we can count. So we have 1, 2, 3, 4, 5, 6 to give us, right, our 6 lobes is, again, what the name is implying, not actually invoking d orbitals. And so then we had looked at our octahedral complex. That's where we had left off. So our classic SF6 here. And we said, so you'll want to get very familiar with this shape. This will come up again too. We'll talk about, like I mentioned, transition metal complexes of octahedral shapes. And so now let's go to the next one on our little Vesper cheat sheet chart here. So looking at what might be a square pyramidal complex. So I haven't given us our example. So then our classic example of that. So go ahead and see if you can figure out what it would look like given our shape. So formerly AX5 with now 1 electron pair. And the classic example is this bromine pentachloride. So kind of sketch that out for me. Again, you're basing it off the octahedral. You know you're just replacing one of these with a lone pair. And so this kind of came up maybe as you're doing the lab, right, is don't forget all those little fundamentals of last quarter of how to build these molecules, right? So always keep in mind, right, your total electron count, so really valence electrons. And so we have, well, all these happen to be 7 valence electrons. So what's 7 times 6?
It's 42.
40.
Did we do the lab?
Well, if you did the lab on Tuesday, yeah. So if you haven't done the lab, so that could be, again, an issue today. So I'll give out some warnings in lab, right? But don't forget your fundamentals. So first, get your total electron count, just to be sure. And then, again, we should have gotten something like we expected. So, again, just taking our octahedral shape. And so, sorry, I don't have the colors correct. But then just, of course, right, removing one. And then, right, using your total electron count to just double check everything. Fill in all our lone pairs. All right, so where are we at? So we have 8 of these, so 8 times 1, 2, 3, 4, 5. So 8 times 5 is 40. And so, okay, yeah, we're missing 2 electrons like we expected from this example that we were given. So yes, it is AX5E here. And so remind me, what's our electron geometry? So that would be your molecular geometry, so what it looks like. So it is square, pyramidal or pyramidal. But then, so what was, I heard somebody say it, what was electron? So octahedral, right, so still from our same octahedral family, again, right, reflective of the hybridization, sp3d2. Everything seemed pretty good on this one. Questions?
Will we get like a sheet of the nomenclature for every hybridization?
I mean, this is,
Oh,
yeah, so this is why you're given that sheet. So, right, I did give you the sheet.
that's the molecular structure. I'm talking more about the electron structure.
So then the electron geometry is always the first one. So yeah, if you want to write that for clarity, right, the first one is always going to match for the electron geometry. So that's our parent electron geometry, and then the specific molecular geometry is of course listed. Yeah.
Did you know the molecular or the electron and the molecular geometry? So for example, the last example was for pyramidal. Is the hybridization always going to be sp3d2?
Yeah. Yep. So yeah, that's good, right? We're just connecting the pieces. So yes, if it's in this family, we know the electron geometry, yes, that is reflective of the hybridization, right? That's why you get that shape.
And is that specifically measured from the central atom?
Yeah, so it's always like what atom you're looking at, right? So we're kind of focusing on these complexes where, yes, they do have a central atom, right? But that being said, so let's look up. Let's do a fun one, LSD here. Trying to pick something that has like chiral centers and stuff. And so basically, right, yes, we're looking at individual atoms, but we want to say, okay, let's look at this molecule, right, and figure out the hybridization. So we could just take, I might as well just copy this over at this point, if I can. And so where we're kind of going with this, oh my gosh. Let's try again. There we go. So where we're kind of going, right, and where you're going in OCHEM is now we can take, so again, I'm going to just look at this nitrogen here. Well, first thing we have to do is, right, satisfy all our rules for drawing stuff. So even though it's not drawn explicitly, what's missing on here that we should draw? Lone pairs. And so don't forget, right, the carbons are kind of drawn hidden. So, right, that's a carbon, don't forget that, carbon, carbon, carbon. But yeah, they also don't show you lone pairs necessarily in OCHEM. And so yeah, that's where you're kind of looking, okay, well, nitrogen has 3 bonds, but I know that nitrogen likes to make 4 bonds. So yes, there's a lone pair here. So now what's the hybridization of this molecule, right? We're treating the nitrogen like our central atom. What's its hybridization?
The
sp3. So now you all are ready for OCHEM. Perfect. And yeah, so that's how you do it. Right now we can examine this carbon. We'll just do another example. And so right, again, in OCHEM, they don't draw all the hydrogens unless it has like stereochemistry here. And so we know we have to fill in 4 bonds for carbon. So there's our carbon. Now it has 1, 2, 3, 4 bonds. So we know it has a hydrogen. Now what's its hybridization? How many things is it attached to?
It's got a sp3, or it's double.
So remember, double bonds don't count. They're just, right, then telling us that we're going to have, so, right, we can already tell, well, there's a sigma bond, and then there's a pi bond, right, because it's a double bond. But then what's its hybridization? sp2, right, because it just has 1, 2, 3 things attached to it. So perfect, sp2. Again, you guys are going to be ready for OCHEM at this rate.
Is there an exception to this rule for hydrogen because it only forms 2?
Well, yeah, so hydrogen just has an s orbital, so right, it's always just going to make sigma bonds. So, and yeah, it's not going to be, yeah, I mean, we're not going to get into like, because there is weird, like, hydrogen can be a bridging hydride, and, but yeah, we're not talking about that right now. So yeah, for the most part, hydrogen is just a point, you know, just an s orbital, so it's just going to be forming sigma bonds. Yeah.
So, certain points in that diagram, they do label the H's, and in others they don't. Is there, like...
Looks like the ones that are sticking out.
Yeah, so this is stereochemistry. So I picked LSD specifically because it has stereochemistry, so I wanted to show that, right? And so anytime we have stereochemistry, that means like the geometry matters. So we're going to talk about stereochemistry in a little bit more. But yeah, that's why these are drawn, because they're trying to show you, yes, this is coming out of the plane and it matters. So that's the thing about LSD. Like, these stereochemistries matter, or else you don't make the drug. That's what makes LSD difficult to synthesize. It takes a skilled chemist to synthesize LSD. Meth is trivial, but LSD is difficult. Anyways, now that we've quickly turned into drug the class, all right, moving.
Maniacs and drug nerds. So are the
All right, so let's look at our square planar next, and our classic compound for this. Any guesses for this one? You might remember this from last quarter. What's kind of in that shape? There's not too many molecules.
I don't know if this exists, but the neon tetrafluoride.
Right family, except, so we can start talking about that. So neon tetrafluoride probably only exists in theory, again, because of just the physical size limitation of neon. And but you're in argon, I think you can force, but the more classic example would be xenon tetrafluoride. But yeah, probably these exist just in like either theoreticals. So I don't know if they've actually made a neon compound, but yeah, I think you can force argon.
So, if I remember correctly, noble gases are notoriously unreactive. Why do they react with fluorine to make bonds? Why do they make bonds with fluorine? I might have something.
Forcing. Well, a lot of it stems from the fact that, again, like xenon is large and fat and diffuse. And so, yeah, under forcing conditions, right, you can get it to accept a bond.
Okay, but it won't do it naturally. It has to be forced.
Yeah, and then so you can draw out, right, the structure. And so we can keep kind of talking about this. So, right, we draw out our structure. So, of course, xenon ends up having 2 lone pairs. And, right, again, we know the noble gases are generally unreactive, since obviously, right, they have a full octet. But then, especially in the cases of these larger noble gases, again, if you just have a physically diffuse orbital, you just have kind of more of a chance of bonding with something. And so, of course, what's our total electron count on our xenon? So 12, right? So 1, 2, 3, 4, so 8, 9, 10, 11, 12. So yes, right, we expect it to be hypervalent. Since it is, again, right, it was a noble gas, started with 8 electrons already. So, and then we can see how 4 of those went into bonding, and then the other 4 valence electrons, right, are still on the xenon there. Yeah.
Does bromine tetrafluoride also, or tetrafluoride, no, pentafluoride, also exhibit hypervalence?
Yeah, so I didn't go over that one, but so right, we could count it 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So yes, also hypervalent. So that's the other thing we're noticing about a lot of these, right? 5 coordinate, 6 coordinate, they're going to be 10 and 12 electrons.
So based off of what you said before, I'm making the assumption that big molecules like xenon can make bonds because the electrons are so far from the nucleus.
Yeah, essentially, yeah, and it's also, it's far and it's diffuse too, right? And so now we're kind of thinking of our electron clouds, because, right, your 1s is pretty tight, right? But then remember, they get larger and larger and larger and more diffuse and nebulous and cloudy. And so, yeah, like I said, these exist probably under forcing conditions or like, very small gas phase interactions. So again, that's what chemists do, right? They really try to force stuff to happen. Okay, well, we know this exists. Why can't we make the higher analogs? And so again, if you look into the theory of these, it all goes back to just a size limitation. So if neon could make these complexes, they would probably have a lot of their fluorines elongated to, again, allow for all of them to physically fit. So that's why they're pretty unstable if you have these elongated bonds.
Do they know what makes the bond unit longer or shorter?
So that's a lot of different things, right? So your bond length just first has to do with the number of electrons, and then its polarity, and then any other things like that, like what orbitals are going into it. And so that's kind of where we're going, right? Like we're already getting there, right? You're already seeing, okay, we can look at a bond, see that it's a sigma bond, it's a pi bond, right? That's telling us what orbitals are coming together. So that's generally what dictates it. And then obviously physical size, but then that's like a big part of research, right? Is, well, what's your average bond length for two compounds, right? And then is the compound that you made, is it outside of that? And what makes it anomalous and why is it cool? All right, y'all are getting me too excited here.
This is a square plane one.
Oh, yeah, square planar. So I got so excited about electrons and orbitals that. So yes, to get back on track, so we said electron geometry is again octahedral, and then yes, like you said, so that means our molecular is square planar. Right. So I think that pretty much finishes off these. So it does give you these other theoretical shapes, but I do not have any examples offhand. I don't know if that could be a challenge for y'all if you were bored enough, but it's pretty difficult to find examples of these. So you probably won't run across this, but at least you have this in theory, right? So again, if you have something with now 3 lone pairs, it's going to be T-shaped again, right? And so that kind of goes back to our earlier question. So again, right, we have 2 T-shaped. So one is under our trigonal bipyramidal electron geometry, and then we have this other, right, theoretical one under our octahedral. But like I said, I don't have any good examples for this one, so you probably won't really see this. Same with this linear compound.
You were mentioning earlier how these shapes mainly apply to gases.
No, well, it applies to everything, but for some of these, it's in the gas phase when they're measured.
Okay. So it can be in the liquid or a solid.
So usually you measure geometry either in the gas phase or the solid state. So kind of going back to like the WebMO thing. So what people do in like real research is ideally you make a crystal. That means you get a coordinate system, right, of all your molecules and your crystals. Then you feed that into WebMO, and then it tells you, or not WebMO, but like an equivalent computational program that would be appropriate, and then it tells you more details and all the orbitals and all those happy things. All right. So that kind of finishes that portion. So now let's go on to the rest of the chapter. And so our second half of this chapter starts to introduce isomers. And so let's kind of clarify before we dive into isomers and what are they. And so this is a lot different. So let's contrast this to to resonance. Because students kind of confuse these two things, and there's a lot of like electron moving around, but they're distinct enough. And so let's kind of, did we ever talk about carboxylic acid in this class? Or carboxylates?
It was on the sheet of molecules for bonding to other molecules.
Oh, okay, but we didn't, so I don't know if we went over the shape. So let's look at that. So this is a carboxylate. So basically, right, a carboxylic acid, which is just an organic acid. So now, let me take another step back for a second. So let's go with vinegar, which is acetic acid, just so we can have some context here. And so these organic acids all have this carboxylic acid group here. So this is called a carboxylic acid. And so why we're looking at this is, well, we're kind of answering two questions. Is we're going to answer why it ends up being a stable acid, but we want to show our resonance. And so an acid is anything that gives up its proton. And so for it to be able to give up its proton, it has to be stable as a charged species. So this is after deprotonation. So after losing a hydrogen. And we're left with this structure. And so a resonance structure is where we can just move electrons. And so we're not breaking connectivity. So that's the key difference. And so what I mean by that is, again, right, we're going to keep our primary sigma bonds. So now we can start thinking about things in even more detail and depth. So we don't want to break sigma bonds. Maybe I'll even add that. So do not break sigma bonds. But we can play with our little double bonds, our pi bonds. And so what we can do is we can move these electrons, and then we will draw our new resonance structure to show that movement. Insert some space here. Oops. And so now these electrons move back up to the oxygen. Now this oxygen has a negative charge. This one is double bonded. And now we're kind of showing why this is a good acid, right? Because now we have this negative charge that is stabilized across two oxygens, essentially.
What does the R represent?
It represents any organic group or like anything. So generally carbons, but then, right, anything can be attached to it. It could be oxygen, technically. We don't want to get too detailed, but it's generally like a general carbon group. All right, so then let's put resonance to the side for now, because we'll come back to this, right? We'll do a lot of resonance just in class naturally. But now we want to talk about isomers. Does anybody happen to know what isomers are?
Isomers are molecules that you can theoretically put it against a mirror, and the molecule you'll see in the reflection can be unique. So any molecule that doesn't have a line symmetry.
So that's a very specific isomer. So you're talking about stereoisomers. So that would be mirror images. So we'll get back to this. But we want a broader definition of isomers. Yeah, Fawn?
They're essentially molecules or compounds that have the same like chemical formula put to when written on paper, but their structures are different.
Excellent. So that was a good definition, right? So same chemical formula, and then, but different structure. And sometimes I like to use the word connectivity, right? To again, contrast it with resonance. So resonance, we said we did not change anything with the connectivity, but with isomers we can, right? So we can completely bust open the bonds, rearrange them, right? Do them in any different ways. And so let's look at that, right? So now we're mainly talking about these structural isomers, right? Where you're, again, really physically separating them and getting completely different molecules. And it could be even as simple, so we have these two alcohols, and so we could verify that they are indeed the same formula. So we have C3, H1, 2, 3, 4, 5, 6, 7, 8, H8, and then O versus 1, 2, 3, and then 1, 2, 3, 4, 5, 6, 7, 8. So O, right? So again, same chemical formula, but different. And so in this case, we won't quite get into organic naming right now, so we'll do a little baby organic chapter like third quarter. But we can already at least start to appreciate it. So propanol implying this straight chain. Sometimes they more specifically put N-propanol to show that it's straight chain. And then the iso group here, that specifically refers to this little structure where you have these 3 carbons in this manner, and you have a little hydrogen here. And so that's our isopropanol. And then our R group in this case is, of course, the alcohol from just our general isopropyl structure. Yeah.
Question, would it be fair to say that the change in the structure of each would change the properties of them?
Yeah, so that's starts to get into, well, how do you distinguish them? So yeah, it can change the properties. These have different boiling points, for example. They would have different, right, remember the NMRs from SOU, so they would have different NMRs that you could distinguish them. They would have the same mass spec though, right? So mass spec would not be useful, so same mass, but yeah, they do have slightly different properties, and that's kind of getting into where we're going with these different properties.
Do they have different densities?
I'm trying to think. They might have slightly different densities. I don't know that these would be significant, but yeah, they could have different densities.
So to get these two different chemicals, like to synthesize it, what's the difference in the steps to get one versus the other? Are they just more like natural? Like, how do you get to those two different?
That's a more complicated question. Yeah, it depends because I actually don't know the synthesis of these small molecules, but sometimes some of these, like especially going back to like how do they make gasoline, right? Well, gasoline is just a mixture of hydrocarbons anyways, and then they start to separate them out. But then it depends on like what you buy. Like for example, the compound hexane. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. This is generally sold as a mixture of hexane. So any isomers are possible in there. So you like really have no idea what you're truly getting. But yeah, and then the synthesis depends on like how you get there, which is a much longer answer potentially.
Typically, isn't there like in chem engineering, don't they use a lot of like bacteria that typically make certain isomers? Like if you want like ethyl alcohols, you would use the like typical fermenting yeast. Something like that.
That might be true for alcohols. Like I said, I don't know like the simple alcohol synthesis. Like I'd be more familiar with like if you're trying to control a stereochemistry in like one specific step, but then usually that gets again very like step dependent specific.
My question directly goes off of that. Are the alcohols, so I know there's a ton of different alcohols, are they all isomers as well?
Well,
Or does it depend on the ones, or?
well, it goes back to the naming, right? So these are all pros. So that means that they have 3 carbons, right? So then you have to kind of figure out, well, how many potential isomers are even possible?
What about, I don't know, I'm trying to think of isopropyl and, I can't remember off the top of my head, but would that
Yeah, because like the problem is like, well, ethanol, right? It's still an alcohol, but then that's a 2,1. Methanol is 1, so that only has one
Okay.
isomer anyways. So,
So
yeah,
not quite.
yeah, you have to think about like each individual alcohol and then like whether it matters if it's structurally different or not. So then, yeah, it starts getting confusing.
I don't know if this is just like a nomenclature coincidence, but I noticed that propanol and propane, methanol and ethane, is there a way to synthesize one from the other? Or is it the same?
Like I said, I don't know the direct synthesis of small molecules like that, and there could be other routes. But you're getting the naming, right? So meth is 1, and then, right, methanol, I just have 1 carbon. And then, Dad, what was your question?
You mentioned that the boiling temperature changes. What is causing that? Is it where the hydrogen is placed on these chemicals?
Yeah, essentially. So that starts to get into like packing. So for example, we can look at these. So propanol, if it's more straight chain, so you can imagine, so 1, 2, 3. So that can kind of stack a little bit better, which creates more intermolecular forces here, versus something that's kind of rounded, right, the isopropanol. It can still kind of, again, get near one another. But yeah, there's less surface area, so that leads to less intermolecular forces, which I believe we'll cover this eventually in here. But yeah, that's what leads to differences in boiling points, is how they can stack. But then again, it goes back into, well, how different are the isomers? How well can you actually separate them out in practice? And yeah, so that gets into all sorts of intricacies. Let's see, where are we doing on time? So let's have some fun. So speaking of isomers, and so I did mention hexane. And so hexane, I'll re-give the formula, so that's going to be C6H14. And then there are 5 isomers of hexane. And so see if you can figure that out for a second. So take maybe 5 minutes or so, work with your partners, right, draw it out, kind of start with a straight chain, and then how many permutations can you make? How can you arrange them? And we'll probably throw them on the board.
Are we allowed to change the carbon backbone?
Yeah, so you can completely change everything now with these isomers. Just the only hint I'll give is, right, don't make any rings. So there's no, this gets into more things, but there's no degrees of saturation. So don't try to make any rings with this. You won't have any luck.
Could they use this reactor to let's say they're trying to come up with sugar alcohol? Is this kind of the same idea to take sugar and rearrange it, or?
Yeah, I mean, usually, like, you start with, like, your sugar, and then, like, maybe what could you add to it? How could you substitute it?
So
Yeah.
I know that sometimes pharmaceutical drugs are the same way, like you can have 2 drugs in the same class, but they react completely differently.
Yeah, but yeah, usually they're like some sort of, like, I know a lot of drugs can be like tryptophan based or something, and then yeah, they just change different substituents. So not quite like isomers, but like you're more thinking of like synthesis at this rate of just like putting the pieces together. Like, okay, you have a small piece, and then how can you change the R groups? Which is literally like all chemistry is, honestly. It's like, what did other people do, and how can I do something that they haven't done?
So we have these for these super like, I guess in this instance, they always
Oh, yeah, yeah. So anytime I don't draw something at the point, it's always part of it. Yeah.
So are all isomers organic compounds, or do you need to have that carbon?
No, so we can have like isomers, so we'll look at isomers of inorganic compounds too. And same thing, so they can have like different properties, different colors, so that's how you can tell them apart. Different like stretching frequencies is called. So.
You wouldn't get, in a structure like this where.
Oh, we're sharing a
Yeah.
hydrogen? No, but
No.
yeah, branching is good.
Yeah.
Like this.
Yeah, but, yeah, don't let the paper fool you, because these are all the same ones, right? So they're all straight chains essentially.
Yeah.
So then how can you change the branch? Because it's going to pop those off. But it's still essentially a straight chain. You're just kind of like not drawing the geometry properly. So like, how can you branch it? Yeah.
Oh, I see.
Yes. Start writing this down, right? You gotta start at 7-1, straight chain, plug it off with someone else. Yeah, so you got your straight chain, right? So now just like imagine popping this up. Put it over here, make it different over here, did you pop off two? Exactly, yeah. Yeah, exactly. So you're starting to see like, yeah, the stereochemistry, each one's tetrahedral. Right, yeah. And then that's great. You're saying, okay, but if it's two, then what you planar. Yeah, so you just get a lot of information. So yeah, that's exactly what you want to see. Like, now we're seeing the 3D structure.
Yeah, I mean, who changes it? As long as there's no like.
All right, let's start putting some of these on the board. And, you know, if you're the first volunteer, you have an easier shot. All right, let's do Vaughn and then Jonathan. Actually, I think there's multiple markers, so you just have to both see if you aren't doing the straight chain.
I'm not doing the straight chain.
Save that one.
Yeah, it's
Are we allowed to do a double bond?
So for this case, again, this goes into like other things, but there's no degrees of saturation, so it would not be appropriate to use double bonds. But yeah, if our formula had been different, I would say, yeah, try it out, but it won't help you here. So I'll copy what we have so far. Oops.
Do I have to
Seriously?
write out every single hydrogen?
No, you don't have to draw out the hydrogens. Oh.
I did just to verify.
Okay. Sorry, I'm trying to copy. All right, so this is the one Jonathan drew. So we have 1, 2, 3, 4, 5 carbons, and then we stuck a methyl group off of the center one. So I just drew it a little flip. Either way, same thing. And so that's the kind of tricky thing about these structures too, is like make sure you're not drawing the same structure. And so I'm going to name these. Again, you don't have to know how to name them right now. We'll, like I said, we'll revisit them later. But you find the longest chain. So 5, so that's pentane. Our methyl's on the 3, so we have 3 methyl pentane for one of our isomers. And let's see, so Vaughn drew this one out. Let me copy it. Slow.
Mine is incorrect. I'll change it.
Yeah, you can change it. I didn't check yours yet. 1, 2, 3, 4, 5, 6, 7. Yeah, I think you got heptane there. And so looking at this one, so to name it, your longest chain is always a 4. So you could go 1, 2, 3, 4, 1, 2, 3, 4. It doesn't matter. But then the naming of this, so 1, 2, 3, 4, B2,3, dimethyl butane. All right, who's got some other isomers? Did you fix yours?
This one's got 13 hydrogens, so
No,
no.
it should be right. Did you count this hydrogen? Because you got
Oh,
the.
yeah, there you go, 14.
All right, sweet. So then we have, let's look at what you drew. 1, 2, 3. So this looks like an isopropyl group there. Or let me see, we can find our longest chain. So 1, 2, 3, 4, 5. So this would be 2 methyl pentane. Yeah.
Could you have what I drew was 6 carbons with hydrogens, 2 on, so it's 6 on top, 6 on bottom, and 6 and 1 on either side, so each carbon makes its 4 bonds.
It sounds like the straight chain to me.
It is a straight chain.
Yeah, so you could do, yeah, if you just drew it out, so then let's just do the straight chain. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Also, word of advice for OChem, count your carbons and then count them again. Literally, right? They really care about every little carbon. So counting is really important. Right.
What's the nomenclature for methyl? Here. So you have 2 common methyl.
Yeah, so it's just 2-methyl pentane to indicate where this is, the position of the methyl group.
On the second atom.
Yeah, so we're saying it's on the second. And then, so I do want to point out, right, we cannot make 4-methyl pentane because that's the same thing as 2, right? So if we did 1, 2, sorry, losing my carbons here. Yeah, this is correct. So if we wanted to do 4-methyl pentane, so 1, 2, 3, 4, but then, oh, look, right, we can rotate it and then relabel it, so 1, 2, 3, 4, 5, so it's still really 2-methyl pentane. Does that make sense?
You always go with the lowest number.
Correct, yeah. So, and any time you can flip it and it's the same one, right, then it's not an isomer, so, right, so that one doesn't count.
Where is the four that you're coming from? What is that counting?
So it's counting the carbons. This is like a little bit advanced, but yeah, how you name it is you count your carbons. So after you find your longest chain, so in this case, right, the pentane, then in OCHEM you want to assign highest priority to your groups. So that's why you call this one a 2, because you don't want to call it a 4 just because it's not high priority. And then like we said, we can rotate so it's the same.
Are you going to put an X next to the 4 methyl?
Yeah, because I'm trying to show that it's bad, right? So this is not an answer because it's the same as 2-methyl. So maybe I'll make that clear, right? So I'll put the X more on the methyl, on the 4-methyl, because we know it's that one. All right, what isomers are we missing? So we have 1, 2, 3, 4. I think we're only missing 1. See. So 1, 2, 3, 4, 5, 6. I'm just confused by your structure. Let me see. 1, 2. So we have 3. That's connected. 1, 2. I think it's this one, right? 1, 2, 3, 4. So I think we've just redrawn. So I think so far we've drawn the same one. Does that make sense? So these get confusing, right? So we can find our longest chain, 1, 2, 3, 4. And then we have, so 1, 2, 3, 4. And then, so this would be the 2,3 dimethylpentane again. Yeah, so, and chat, yes, you're correct. So we did draw the same structure. And again, right, that's okay, that happens. We're pretty close though with this one.
Can I give it a hack?
Yeah.
Then you've got a leg that's too long. Then it goes 1, 2, 3, 4. And you've got a 2 long.
Yeah, because now you redrew it, so you have 1, 2, 3, 4, 5. So we're back to 3-methyl. But what else could we do with this?
Just do like the straight line.
So not the straight one, but because we can't do 2 and 3. But what were you saying? Yeah, so you're saying like 2 coming out of 1?
Yeah.
Yeah, so this is the one we're missing. So yes, that would be 2, 2 then, which is kind of funny. Dimethyl butane. So yeah, a little tricky, and then you make this little, I can't believe I blanked on what this is called. Because it's about the longest straight chain, so 1, 2, 3, 4, right? Because these are both branching off. So yes, that was the last one. Yep, and then the straight chain, sorry, I drew it up there. Alright, so yeah, so that was our straight chain, so 1, 2, 3, 4, 5, 6, and then I specifically put N-hexane, again, just to indicate that it's linear, since like we mentioned, right, there are, well, 5 isomers of hexane, so if you purchase hexanes, it is all these mixtures in hexane. All right, so let's take a break. So I lied about being able to finish, but we don't have too much more. So yeah, we'll continue with a little bit of chapter 8 after our break during our recitation time, because like I said, we don't have a quiz. So yeah, go ahead and take a 10-minute break. We're running a little late. So probably let's get back around 12:10 or so for lecture, or for the rest of lecture, whatever.
I came up with this at the very end. Can you also do, right up there, can you also do this one?
Let's see. So we have, what's our longest chain? 1, 2, 3, 4. That, isn't that the one we just drew at the end? Or am I looking at the wrong one?
That's the one that we just drew at the end.
Yeah. So then which one did you draw?
This is, I'm just
Yeah, that's
coming
the
up with
same
that.
one.
Is it?
Yeah.
Oh, yeah, yeah.
So yeah, you came up with it at the end.
Great. Oh, sorry.
Sorry.
Oh, I had a question for you. I was going through my biology book, and I came up with a question about. So they do like they do the carbon dating and radioactive decay and everything like that. And they mention how through like the radio. I wrote the question down. Now I can't find it. Okay, so with the radioactive decay, it's based off of the element turning into like argon, and how what they use. They use potassium decaying into argon, and when I think about argon, it has the 8 valence electrons that kind of complete the shell. And that made me think about, well, what happened to the proton that was in potassium what happened to that proton? And then is there like a structure just like the 8 valence electrons that protons will have that is like that really nice, significant structure that keeps it really stable?
Yeah, so that kind of gets into like radioactive decay.
Mm-hmm.
I was trying to think when we do that. Because if we go potassium to argon decay, I was just trying to figure out if it's, yeah, so this gets into like the different times of decay. So right, then we have to learn about like beta decay and what that is. And so that means, right, like you're saying, your different subatomic particles and breaking up into different things, and then they get lost and become different substances. So that's what's going on.
Right, losing that electron and then.
Maybe that might be, because remember you registered for classes with me.
Yeah.
I guess the whole thing kind of breaks apart into individual qualities.
Yeah, because if you look up, because, right, all these different radioactivity just has to depend on the types of decay. Let me just find. I'm just trying to find a nicer, like, cheat sheet for this. But yeah, we'll talk about this eventually. I want to say it's this quarter, but.
Okay.
That's what I.
What a nice loading animation.
I don't know why it's so slow. Seriously. I was just trying to find like a nice chart that wasn't a bunch of stuff to read, other than pulling out my notes, which I was refraining from doing. Yeah, because like, you know, alpha decay, that's whenever you lose your helium. nucleus, right? So then you're losing 4 mass and then 2 protons. And then, right, you go to beta decay, although there's different types of beta decay. So then there's 2 different types. So you have your beta minus, where you have the neutron goes to a proton, and then, right, you also create the electron that's ejected. And then, or you could have what's beta plus, where your proton goes to the neutron, so then you get a positron. So that's what's going on.
Are those like stronger than the ionization level requirement for those electrons?
Yeah, so those are pretty strong, like, energetics of what's going on, right? Because anything that's radioactive has pretty high energy density, so those are really strong, like, fundamental forces that are being broken. But then we'll also kind of quantify those as well, because you'll see, we'll get into, like, the mass effect. And so basically, right, E equals mc squared, so that small bit of mass effect is from anything that was lost.
Okay, gotcha.
Yeah.
Cool. Okay, thanks.
Okay, I looked up isomers and I got overwhelmed. So, are we gonna go over the stereoisomers versus the constitutional? These are all constitutional.
Yeah, these are all
right?
constitutional. So yeah,
Okay,
we'll
then
talk
what is
about.
stereo? Like,
Well,
I'm not.
those are mirror images, so we'll talk about that, like, briefly in
Okay,
here.
that might be more of an organic chemistry
Yeah,
question.
so
Okay.
it'll continue more for OChem. Basically, for our purposes, we just need to know that they're mirror images. We'll do some practice in lab, but yeah,
What's an
OChem.
example of like a stereoisomer?
Well, I mean, your hands are a good stereoisomer, but
Okay.
yeah, even going back, so that's why, like I said, I had picked LSD to look at, because then we can say, well, that's a stereo center, that's a stereo center. That's why they bother to put those wedges and
I
dashes, because it
understand.
matters. Yeah.
That makes, okay, I missed that.
No, there's a lot.
Okay, thank you.
Yeah, I think you do. Yeah, well, no, it's 97502. I was like, it's either 03 or 02. I think 03 is.
Oh, I think, yeah, quiz pile.
Okay. What about me? You didn't even last year. Yeah. I'll probably use it back in and so it just depends on if I do it in 6 years or more, which I'll probably leave it in more. It's probably gonna be, I'll probably 8 years. Yeah, I was like, if I take a gap year, I'm never coming back. Like, I'm just gonna keep pushing it off. Yeah.
So much just happened, I don't like believe it. No matter what. Yeah, but
Oh wait, they don't open till February 1st or anything. I'm gonna look at it. I don't know what it's like. We'll get faster. I think you have to get a person to pick it up. Yeah, I know that.
It's really annoying. I have to drop my phone. Please. Don't go like this.
You okay, Anna?
Yes, I'm joking.
Okay, I didn't, joking, talking out.
Oh, I forgot OSAC.
Oh, yeah, you can, yeah. Put on the file.
That's why it's using it. It's using whatever promises. And then you still have like power much. So you're going to see so you can
Is this assignment or is that like a reference sheet?
Oh, that one's the homework. So yeah, it should be up there if you didn't grab it.
I thought it was the class term and then
Oh, the metric or the,
the conversions.
yeah. All right, did we make it back from break? So let's finish up with our isomers that we were discussing, sorry. And so, okay, we did our structural isomers. So like we said, complete different geometric arrangements or spatial or connectivity. And so now let's look at the more specific example, which we had been given kind of an example. And so we had gotten into this stereoisomers talking about mirror images. And you can, right, start off with your hands. That's your simplest mirror image, right? You can try to superimpose your hands, right? You can't do it, but they are mirror images. And so that is the official definition of, well, let me correct myself. So stereoisomers are more specifically different spatial arrangements. And so this kind of gets into more specific OCHEM stuff, like diastereomers, which basically, to give a quick rundown, I'm not doing a very good job, but a diastereomer would be where you have kind of two stereocenters and one's an R and S and the other's an R and R or something. But save this for OCHEM, right? So save for OCHEM. But we want to focus more specifically on these stereoisomers called enantiomers. And those are the mirror images. And so the full definition would be non-superimposable mirror images. So that's what we'll be focusing on in this class. And, sorry, was there a question? Enantiomers. So non-superimposable mirror images. So again, we're just focusing on one stereocenter with these enantiomers. No, question?
Yeah, can you have enantiomers that exist in multiple dimensions, like a Y and an
I don't quite.
Like you have the chirality and how a molecule can be non-superimposable, just reflected across one direction. Can you reflect it across another direction, like kind of another?
Oh, like two mirror planes?
Yeah.
No, you just have like one mirror plane. Because if you have multiple mirror planes, then usually you have a high order of symmetry. So then, yeah, it would be symmetric in some fashion. And so let's look at like why enantiomers are important and why we should be aware of stereochemistry. And so I brought up this case of thalidomide. So this was, I believe, in the 50s or 70s. And so what happened is they started to use it to treat the symptoms of pregnancy, so nausea, and yeah. So blah, blah, blah. So first marketed in 1957, right, over the counter, and right, prescribed for morning sickness. And so this is where the controversy arose, right? So again, this is why safety testing is super important and everything, and drug development is difficult. So right, they thought it was safe, and then concerns since, right, birth defects started to arise, and then, right, people were trying to figure out, well, what is going on? And so, right, a lot of people were horribly harmed, and so, right, that caused it to be pulled from the market. But then, okay, now let's think about it from a drug development standpoint. It's like, well, what happened? And so let's see if I can find where it gives us the explanation here. Blah, blah, blah. Where does it tell us? I was trying to, and so, let's see. Okay, here's what I was looking for. And so the issue is it's a racemic mixture of the two enantiomers, and we'll go back and kind of look at what that means. But then there's also a second issue, because then, right, it mentions, okay, well, there are reports that only one of these enantiomers may cause birth defects, but here's the problem, that your body converts the enantiomer into the other form. So essentially, right, even if you feed somebody the correct enantiomer, your body's still going to change it, so it's still going to have those toxic effects. And so, right, there's the conclusion there that the safe R thalidomide undergoes chiral inversion. And so this is kind of answering at least some of the questions of, well, how do we change chiral centers? And this doesn't always happen, but it just so happens that this compound, for whatever reason, and I don't know the exact mechanism of this one, why it's susceptible to changing, but essentially, right, your body is going to flip the chirality, so even if it was the R, it's going to convert it to the S potentially.
Is this common with anti-nausea medication? Because I had a friend, she had babies, she had HG, don't remember what it stands for, but severe morning sickness. She couldn't get Zofran for it. Because I think it was, I don't remember if it was similar, but apparently there's an increased risk of birth defects for that one too.
Yeah, I mean, so that starts to get into like the whole rabbit hole of like,
I can sorry.
no, I mean, but that's perfect because that is like the question, right? And so that's kind of a problem. I think that there are studies that show that Zofran, especially when taken in the first trimester, could potentially lead to birth defects. Minor ones, like I think cleft palate.
That's what I heard.
Yeah, and I haven't dived deep into the literature enough to confirm this, but I've heard some reports that like Zofran could potentially be blocking nutrients to the child, and that's what accounts for the birth defects. Again, I don't know, right, all the mechanisms. So that's like the problem. Now we get into like the problem with drug development, right? So let's just think about if you're doing a reaction in chemistry class, right? You're doing it in a very controlled environment. You got your beaker, you're adding something, right? You're seeing what's happening. Your body, though, right? When you turn your body into the giant petri dish of chemistry, right? You got all these equilibrium reactions back and forth. Not to mention everybody's body, right? Process things at different metabolic rates. Blah 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 blah. So all this chemistry starts to get much more complicated, right? So that's where.
With liver, it breaks things down. It's not necessarily in a way that it's going to show in lab. Right? 'Cause I
Yeah.
heard the same thing about ibuprofen, that they thought ibuprofen was perfectly safe and fine, but then they saw that I forgot exactly what the study said, but the way it breaks down the liver can cause problems.
Yeah, so that's where like, so then if you're doing drug development, you kind of have to study, so then you put it into the person's body and then hopefully measure like the urine output and then like what compounds are in there, but then of course, right, that goes into what's water soluble, so yeah. Yeah, it gets complicated, but that's where it comes from, is like, yeah, then you try to understand, well, what were the byproducts of that medication, right, that the person has excreted out, and then what does that tell us about how the body process, right, that medication. So there's a lot of things there. And then we'll skip this for a second because that's the paper that I have, but that we might get into the rabbit hole of like other discussions. So let's skip to our easier isomers before we go down the rabbit hole. And so looking, oops. I think I dropped, oh, here they are. And so we have our different isomers. Sorry, I'm trying to make sure I put all these things. Okay. So we have, let's look at, back to our octahedral complex for a second. And so we have, notice the general formula here. So we have X4, Y2, right? So we have two different substituents. And in this case, our two substituents could either be next to each other in this 90 degrees, and that is known as the cis isomer, or we could have them directly across. So we're going to have different effects, and that would give it the trans isomer. And so going back to what we were saying, okay, do these isomers, how do we distinguish them? And so right in this case, obviously they would have the same mass, but they would have different electronic properties because of these, whether or not, right, they're on the same axis. So notice in the trans, the two chlorines are on that Z axis, as I would call it, and so that's going to give it a different effect versus when they're cis.
Can also be used as a means for filtering isomers out.
So you could like measure them, so they could potentially have different like color bands. Then because of those electronic properties, you could measure their stretching frequencies. That
We can take like a magnet and pull them out.
no, so that's the trick though, would be separation. These would probably be pretty difficult to separate, at least I would imagine. But you could, like I said, probably characterize it still. And then, so this is kind of going with your lab and what it wants you to get at with these complexes. So now we're saying, okay, if we have a square planar complex, I don't know how that piano's so loud. I think there's a piano in the other room.
That's driving me nuts. I thought I was imagining.
And so right now we're looking at these complexes of AX2, Y2. And so again in lab, right, we could have them directly across from one another as again the trans isomer, or if they're next to one another, that will be the cis. So this is cis platinum versus trans platinum. And again, right, I might expect them to have slightly different properties, electronic properties, so then you could distinguish them. And then the last important octahedral ones that we should go over are these FAC and MER ones, except your book calls them differently, which is kind of funny. So again, these are for octahedral complexes only. And I made two different molecules so we can kind of pass those around while we continue talking. And so we have the FAC here on the left. And so FAC kind of refers to more like facial. And so the key is, and I oriented it this way so you can see, but basically we can have, and they drew a plane here, but we can make a plane between three of our same atoms such that, right, it just sits on that plane. Now your book calls it something different, which is confusing to me. And honestly, I'd never heard this name until your book referenced it. But I'll kind of redraw it now. So redrawing, so chlorine, and then chlorine, chlorine, and then, right, ammonia. And so this isomer, and so you can kind of guess maybe what your book calls it, because what's the relationship between this chlorine and then chlorine and chlorine? Remember what we just called that above? Yeah, cis. So your book, again, I have only heard of the term FAC, but your book calls it cis-cis isomer. So just be aware of that. I think you'll run into FAC more in practice, because again, that's what the term I'm more familiar with. But just be aware that your book calls it cis-cis, again, showing those two relationships. And then the next one, so the second one is MER, and you can see, right, it kind of is on the same plane here. And then two of them, right, are now across. So I'll go ahead and send these around. So just pass them around so you can kind of, again, see the difference. And then I'll redraw the MER isomer so we can see what the book calls it. So again, right, two of the chlorines are now across. And then, right, one of those other chlorines is in the axial position. I don't know if the stream can hear the piano music, but yeah, distracting. Anyway, so your book calls this one the cis-trans or trans-cis isomer, since we have trans and cis. But again, like I said, you'll probably encounter MER more commonly. So MER, or again, trans-cis, as your book refers to it. All right, how are we doing on time? Okay, I'm going to hand out this Actually, let's talk about your paper. I'm all over the place. Let's talk about your paper briefly before we go on more tangent discussions. Oh. Sorry, I closed my Blackboard right as I was about to use it. So did everybody grab the paper guidelines? And then if you're online, they should be posted.
Where are they online?
It should be paper guidelines right there. And so obviously the date's a little off. Everything else should mainly be okay. So the goal, so like I said, right, third quarter is when our final 5-page paper is going to be due for this. But right now we're just at least focusing on a 3-page draft by the end of winter quarter, right? So the other point is we're trying to develop our writing. So right, we're going to make a draft this quarter and then edit it for spring and then of course do a poster presentation. And so it mentions that here, that again, right, we'll resubmit this paper in spring, so long-term project, and then, right, we'll increase the paper from 3 to 5. And if you make it 5 for this quarter, right, that's just less work for next quarter, so just keep that in mind. And I'm not going to be as strict as these guidelines, so these guidelines, right, are mainly like a good starting point. But again, you know, if you have a good idea, you're a stronger writer, feel free to, you know, restructure this. And so kind of the idea is you want to use 2 primary articles. So write actual journals of what's going on, the experiment that they did. And ideally kind of 2, either kind of comparing that they're doing the same method, or if you want to do, right, compare and contrast. But like I said, feel free to have fun with this. So, you know, if you want to take it to patent law, then, you know, study some patent laws or some case law reviews. Like, that would be interesting too. Like, I want this to speak to you and be in a field that you're interested in. And then again, right, I'm not going to be grading you strictly on this, but this is just kind of a general idea on how to write a paper, right? You want to give some sort of introduction. What's the relevance? Why do we care? What are you doing, right? Are you comparing and contrasting? Are you arguing for a certain point, right? Are you just looking at a certain synthesis? Are you comparing different antidepressants and how they're similar and effective, right? Just what's your thesis? And just make sure that it's succinct enough that you can kind of get into it, right? So you don't want to be too broad of a topic. And then, right, research methods, that's where you want to get into the paper and, you know, make sure that it's at a good level that you can understand and interpret what's kind of going on and read about it. Because I know some of these papers get pretty dense too. And then, right, interpreting, you know, were they good results? What do you want to say? You know, you could get into energy, blah, 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 effectiveness, Hunter, and then.
One issue I have with reading scientific papers is that they often cite things in sort of an endless chain. Like you'll read a paper and it mentions another author from like 1995, and mentioning another paper from the 80s. And so when you're reading a paper, how do you know when to stop, date, or like sources?
I mean, that is the existential question of being a researcher, right? Like, so that's just where you have to kind of do your best, right? To kind of answer, well, what question are you trying to understand, and then what's like the most relevant information? Because yeah, like you said, it's easy to go down the rabbit hole. I've certainly had to do that in my career. I've ended up trying to read German papers, and I'm like, why didn't I learn any German in my life? Like, so yeah, you can easily fall down the rabbit hole, but that's why it's like, what's your topic? Kind of stick to it, right? And then if you get lost, so in the literature, you're having trouble, you know, ask me for help, because then maybe I can kind of help you find a good paper. Because yeah, otherwise, yeah, you can endlessly read the literature, and like every professor has that philosophical like crossroad of how many physical papers can I read, right? Because you cannot keep up with all the literature. Like that's.
Is there like a specific class of paper that limits the amount of cited sources?
No, no, that's the problem, right? They're going to be citing it. And as you keep going on in science, right, they're probably going to be citing more and more stuff. So it gets crazy. Anyways, and then we want it to be, oh, sorry, yeah.
Yeah, I was just wondering if you had any good recommendations for what types of places to like find current or like view.
ACS, right? And that's why I brought all these CNN articles, because these are good inspiration, right? What's going on, what's relevant, and then, yeah, just getting into the journals. And like I said, obviously we only have access to CHEM Ed, but that's why you can email me, and I will get you the papers that are paywalled.
You, I've also found a lot of success with like when researching topics to go to YouTube and like reputable YouTubers who talk about science journalism and then look at their cited sources for papers.
Yeah, that might work, but again, you might have the issue of just, again, running into primary sources and they're paywalled. And then, so yeah, ACS format, and then it should be double spaced, right, 3 pages. And citations. And then this is just kind of giving you an idea of, again, topics, but hopefully you explored some topics at the end of last quarter, and then, right, you're continuing to explore, either refining your topic, getting a new topic if you realize, you don't like it anymore, that's fine. And then, like I said, just re-email me if you need articles, right? Because I don't want to go through last year's Blackboard and try to figure out who's in this class and who's not, and what articles you need. So just re-email me so I can get you fresh articles. Oh, and then the only difference is this date is wrong online. I don't know if I have the original to fix it, but I gave y'all an extra week, so the deadline will be January 31st, but I need to fix that on Blackboard anyways. And I'll probably do just like a topic check-in on Blackboard too, or maybe by paper, just to at least kind of see like, what's your topic? What are you thinking, roughly? All right, so there's our paper. So let's go back to the rabbit hole of fun. So let me hand out this article. Oh, click it down the line.
Oh, okay.
Yeah, I might have lost count. All right, so, on. Sorry, give me one short. Anybody else that I leave out? Oh, you didn't get one? All right, so I wanted to at least look at this paper and again, kind of talk about it, give you things to think about. And so the context of this paper, well, actually, right, this is a good exercise in going through the abstract and kind of figuring out, right, how they write an abstract. And so, right, it mentions understanding the single-handedness of biological molecules has been of intense interest since Pasteur first separated mirror images crystals of tartrate salt. And so, right, we all know that, right, that life has a handedness to it? Yes? No?
There's, I think it's grapefruit and oranges, they have the same chemical, but it's converted, so stereoisomers. Is that what you're talking about?
So that, I think now we're talking about terpenes and terpenoids, but, which is kind of the same, but not so we're talking about like amino acids, right? So like all your amino acids in your body, I believe are left-handed if I remember correctly. Those of you who are more biology-minded, help me out. And then I think the sugars are all right-handed.
I heard they were trying to make a mirror line for it, so
Yeah, so that's why I brought it up. Actually, was because of that. Because this always comes up, right, as mirror life and I don't know, all these theoretical things. So yeah, so basically all our amino acids are single-handed, right? So all left-handed. And then all of life is based off of that. And so then so that's the context. But then the question is okay, let's say if we're trying to figure out how we may have evolved from a primordial soup is, okay, well, where did chirality come from, right? So if you're just given all these fundamental building blocks of atoms and molecules, right, why is it that life, though, only exhibits one chirality? So that's the problem, or the question, that we're trying to answer. And so this researcher, Norden, does a lot of work on this. And so basically what they were trying to do is figure out how you can kind of first convert between the two isomers, because again, assuming that you have this primordial soup, right, you should, in theory, have a racemic mixture, right? So 50-50 of R and S. Does that make sense so far? And so then what they were trying to do is figure out, well, first of all, how can we go back and forth between these two isomers? And so they kind of perhaps cheated in some way. So again, I'll let you all make your own kind of conclusions for this primordial soup or not. But basically, all amino acids, and let me pull up another chart of amino acids here. But all amino acids, so they have this chiral center, at least most of them do. Only one of them does not have a chiral center. But most of them have this chiral center, and we can essentially break the chirality. So it's not shown here, but there's a little hydrogen there, right? So we have 1, 2, 3 bonds. That's a carbon. There's a hydrogen there. And so what's shown in scheme 2 here is basically how we can go from one to the next in this case. So in this case, we have a proton, an acidic proton, so it's susceptible to deprotonation. But right, he kind of cheated, maybe, essentially. Again, right, this is where you can start to criticize things, because they used a base. So DBU, y'all wouldn't know this, but this is just a base, right? So they used a base to essentially get that deprotonated, and then that allows it to either reform, we're running out of time. That allows it to reform either as the S, right, if it comes back on in the same manner, or it could flip it and make the R chirality. Okay, so that's kind of, chirality goes back to the handedness, right, left, right, so it's different enantiomers.
The molecule looks different in a mirror. It's a really different structure in a mirror than it's chiral.
Yeah. Sorry. If you look up, I'll print this out for third quarter. I don't know if this helps. This is a nice picture. So these are all the amino acids. So again, right, we're seeing that they have stereochemistry. So there's a stereocenter. Notice glycine, that's the one that I mentioned that is not chiral. So it just has hydrogens there. But every other amino acid, right, has a chiral center. So then, right, it has a mirror image. And so basically, I'll summarize this paper since we're running out of time. Basically, what they try to do is figure out how, again, from a primordial soup mixture, we could get one crystallization. And his kind of conclusion, and they do their experiment with also some glass beads, right, to try to kick up the energy, speed up the process, right? Because that's the other problem with this experiment is we're trying to potentially do billions of years of evolution or whatever in a little petri dish really quickly, right? On a time scale so they can publish and move on with their lives. So that's what they try to do. So, right, we're doing these mixings. And then their kind of conclusion, and it goes into this Oswald ripening thing, is that maybe at some point the left-handed crystal amino acid kind of came out of solution, and then that's going to drive the formation of more of it, right? And so now it's saying, okay, it crystallized out. Now we have our base where it can go back and forth, but if we lose some of this to crystallize out, then maybe more of this conformer, right, will go to the L chirality, and then just continue, right, to crystallize out until essentially life has one chirality. Yeah, I mean, so that's what's happening is they're just inverting that center. But then, right, you can, and this is where you can guys debate this philosophically after, is like, is this realistic, right? Do you see crystals of amino acid just forming in nature? Would that ever happen? Would that really lead to, you know, life? Or, you know, this is where we get into maybe was there intelligent design? So then you can get into the, right, that whole debate of intelligent design versus primordial soup.
Is there like a rule of thumb of how to determine the chirality point on like the amino acids? Like,
oh, it has to have 4 different things attached to it. So that's the other time, you know, it's a chiral center where there's 4 different substituents. And then usually the key is they bother to make dashes and wedges to show that, yes, the orientation, spatial orientation matters. But yeah, you can, you know, again, I think we're kind of running out of time here. But you can read this, you know, kind of see. I mean, this is a real experiment, right? They did an experiment, they got published. It's an idea, it's a theory. And then like you had mentioned, right, people are talking about, well, can you make the mirror life, right? So if you made an amino acid that was the different chirality, which they do, right? So you can start to construct different amino acid chains that are synthetic and of the wrong chirality. But then the question is, right, could you make a whole protein of that? Could you make a whole life of that? And I mean, that's very like theoretical at this point, but you know, people talk about it.
So is the thesis that like if it was, you know, a primordial soup or, you know, probability or whatever, that it should be able to create the mirror life?
Well, that's the question, right? Because, well, that's the result, is we have the mirror life, but the question is, how did the primordial soup, if we were indeed a primordial soup, how did it become one-handedness and chiral life? Yeah. So again, that's where his thesis, you know, says this, and again, right, this happened on a billion whatever time scale, yada, yada, yada. I'll let y'all make your own debates and conclusions. All right, I'll stop talking, and then if you didn't have lab on Tuesday, you can see me today, obviously, at 1:30, same place. And yeah, otherwise, have a good weekend.
Is that for soccer?
Sorry?
Is that for soccer?
Oh, yeah, I'm just wearing it for spirit, you know.
I was going to join soccer next year.
Oh, you should.
Yeah. I think it'd be fun.
Yeah.
Makes sense to me because in the primordial soup theory, molecules grew to such a big extent with RNA that self-duplicated with.
Well, I think we're talking about even before RNA, right? Because how did you even get chirality to get RNA? Because that's the problem. Is like we're even at more fundamental soupiness.
Like, you know, the digestive nature of life could have like broken down one over the other, and it would have quickly overwhelmed it.
Well, I would assume there's no digestion at this point, but that's where you can go philosophically debate. Yeah, it's like, what if you literally just started with atoms, right? And then you had to start building stuff.
I had a question about the pi and sigma bonds. How would I determine those from this equation?
So remember, we kind of like briefly broke it down, so like if it has one bond, that's the sigma bond. And then if it has two bonds, then it's gonna have a sigma and a pi. And then a third one has to be two pi's then,
So
and a
like
sigma.
this, or this would be a sigma bond because it has a double bond there.
Yeah, so it'd have a sigma and a pi.
pi.
And then you would count, so the way you have it would be 1, 2, 3, 4 sigmas and then 1 pi. 'Cause, yeah, 'cause
So
you,
each bond is different.
yeah, so it wants you to count like the total number.
Oh, okay.
Yeah. Yep.
Yeah, I just need
Did we run out? Oh, do you have Lavender by any chance? Let me go print it out real fast. And then, any questions online, just email me, please. I'm gonna stop this real quick. Otherwise, see y'all in lab.